Good morning, class. I hope everyone is doing well. Friday, so is the last day of school this week, and we have the weekend to look forward to. But let's finish strong this week as we have a quiz and Bible class. So we're going to pray for that. I'm going to dismiss you, and then you guys can go ahead and I'll come down there and hand you out the quiz and class. But those who are distant learning, it doesn't look like anyone's on. I don't think anyone is on. What is going on? Hello, hello. All right, it looks like we have someone just said 0 viewers. Sorry, I didn't know if you guys were on. Okay, but we have a quiz today. I believe I sent that to you, distant learners, those who are tuned in. If I didn't send you the quiz, let me know. I'll get that to you. I'm pretty sure I gave it to you, but if not, I'll get that to you as soon as I can. It's just over this lesson 2 from this week. I'll be down there in the classroom to help monitor that real quick, and that's all we're doing for today. Okay, so I challenge you, after you take the quiz, to read a Proverbs or read a Psalm. It's a good thing to start your day, get a little of God's Word in your heart. But let's pray real quick for you guys and for the weekend. Dear Father, Lord, thank you for this day. Thank you for the beautiful weather you have given us, Lord, and just another day of life, and also be able, the opportunity to be able to be here at CCS, Lord, with all the craziness going on in our world, Lord. You've given us a place we can go to, and we can be with friends and peers, but also still learn about you and further our education. Please bless today, Lord. Bless all the students here. If any quizzes they have today other than mine, also please bless them on this quiz, Lord, for them all to do well, to remember what we talked about this week and hopefully what they studied. Please give them wisdom and strength for the day, and then to get rest and to have a little fun over the weekend. Bless this day, Lord, and we love you so much. In Jesus' name, amen. All right, we'll begin that quiz. Once I get down there and hand those out, distant learners, if you have it, start it. If not, let me know, and I'll get that to you. All right, well, have a good one. What up? Long time no see. We're gonna do some notes today. Ooh, wrong password. So let me get up those slides for you guys. We're almost done with this chapter. If you know what that means, okay, this is chapter 3. I told you at the beginning of the year. We'll have a test every 3 chapters. And we're almost done. So what does that mean? It means we're going to have a test soon. I believe it is next Wednesday. We'll be finishing up the notes. I think on Monday we'll finish up the notes, and then we'll review on Tuesday, and then we'll have our test on Wednesday next week. I believe that's what I had scheduled and I put in my lesson plans for next week, but not 100% sure right now, but I'm pretty sure. But let's see. Oh, we did that one, so we're on this one. Yesterday we were talking about our nation being born, right? It started with the Great Awakening and us creating our own morals. And then we had, then it went into like Benjamin Franklin, talking about the Albany Plan and having these ideas that weren't passed but were going to be used later. George III came into the picture. He ascended to the throne. And remember, he was trying to push his power back onto the colonies because it wasn't contributing to them very much. They were kind of just leaving them alone, letting them do their own thing for the most part. And then we had 2 men, William Pitt and Edmund Burke, we talked about. There are 2 English parliaments who were on the side of Benjamin Franklin, John Adams, George Washington, right? They're on the side of the colonies. Because remember, we talked about how there's people in the parliament that would be working for the kings, and they'd be called the king's friends or something like that. And they'd be working, trying to push the king's agenda in the colony's parliament. Okay, then we were talking about how Parliament passed a thing called the stamp tax, right? They're trying to charge them for sending any documents or newspapers, and they'd have to get a stamp, and it'd cost money. And with that, they made the Stamp Act Congress, and this is delegates from the 9 colonies. They all met in New York, so this is like the first big thing. They all met in New York, except in Georgia. Remember, they all met except Georgia. And this required the colonists to purchase. They're here meeting and to discuss this act. And then they had the Declaration of Rights and Grievances, and this was issued by the Stamp Act Congress. And it was a protest against the stamp tax. Remember, we talked about that. And other British regulations that they're putting on the colonies. There's like, hey, we're under you guys. We'll obey you and stuff. But, man, you can't make us do all these things and charge us for nonsense, right? They're saying, hey, you're pushing the boundaries. And they were saying, hey, we're still free men, and we're here. And with all that, there was going to be conflict back and forth between a little bit with the colonies and everything. And then we had the Intolerable Acts. This is the series of laws Parliament enacted to punish the colonists. Remember, because, again, we had conflict, and then British was trying to put their will in making people buy their products, their tea and everything. And you have, within that, we didn't really talk about it, but Boston Tea Party. And in that, the Intolerable Acts were made, and these were, they called them intolerable because the colonies called them Intolerable Acts because they're intolerable. They're too much. They were asking for too much. They were pushing this agenda, remember? So it was a series of laws that Parliament enacted to enforce that. And then we got into the First Continental Congress, and this is made up of delegates, again, everyone except Georgia, and they were pledged the loyalty to the colonists rather than to the crown, or to the colonists and to the crown, but they protested Parliament, the people pushing the king's agenda. They said, hey, we'll be loyal to Britain, we're under them still, but we're not going to obey these Parliament guys. They're doing too much. And again, that led to conflict, back and forth, back and forth. And then about 10 years later, we had the Second Continental Congress that we mentioned yesterday. This convened in Philadelphia on May 10th, 1775, and it began to assume political power, okay, this idea of Continental Congress. They were trying to build an army then, support an army through it. They appointed a commander-in-chief, which was George Washington, and they issued money. Okay, they were asking a little bit of money from all the different colonies and groups of people to fund this, okay, because they knew after this fight that Britain would be coming. Remember how we talked about on April 19th, so slightly before this, 1775 at Lexington, the shot that was heard around the world. Remember how we talked about that? From all that conflict and from the Intolerable Acts and the First Continental Congress, people and the colonies boycotting the British. This led to the shot heard around the world. And this led to King George. Remember, he said, no, or the colonies still try to have peace. Like, hey, we'll still be under you. King George was not having it. He said, no, this is a declaration of war, and you guys are now enemies to the crown. And we left off with that, and we're going to start our notes here. Oh, I got to put them up here. Start our notes here, so pull out those. We're talking about the Prohibitory Act. The Prohibitory Act. So we have, in August 1775, the Congress, still hoping for a peaceful resolution, as I just mentioned, between the colonies and the crown, made one last petition to George III for a redress of grievance. Not only did the king refuse to receive the petition, remember, he was like, no way, you guys are enemies to the crown, but he also proclaimed the colonies to be in rebellion and virtually declared war on them. In December, Parliament, at the king's urging, remember, they're the king's friends, they're helping him out, so at the king's urging, determined to ban trade with the colonies. So all the products that Britain was giving to them or selling to them, they banned the trades. They took it all away. So colonies would be left alone until the troops got there for war. The resulting act, known as the Prohibitory Act, and again, this was passed by Parliament at the king's urging. It cut off all trade between the colonies and England and removed the colonies from the king's protection. Okay, this removed them from the king's protection. Thus, over 6 months before the Declaration of Independence, both the king and Parliament dissolved their relationship with the colonies and declared England to be at war with her former colonies. By early 1776, many Americans believed the king had left them with no choice but to declare independence. Okay, so basically, the king had said, no, I declare war. You are virtually in rebellion to the crown, and this left the colonies with no other option. Remember, they were still trying to have peace. They're still trying to work out some kind of middle ground where they could have freedom, but they would still obey and respect the crown. But they couldn't, so this pushed them and made them to have to make the choice to declare their own independence. Again, over 6 months before the Declaration, as I just mentioned, both king and Parliament dissolved their relationship with the colonies and declared England to be at war with her former colonies. And then by early 1776, many Americans believed the king had left them with no choice but to declare their independence, okay, as I just mentioned. So moving on to that, we're going to be moving into the Declaration of Independence. So on June 7th, 1776, okay, so this is right after Americans declared, hey, we're going to have to declare our own independence. Richard Henry Lee of Virginia presented to the Second Continental Congress a resolution for independence. On June 7th, 1776, Richard Henry Lee of Virginia presented to the Second Continental Congress a resolution for independence. But he said this, Richard Henry Lee said this, resolved that these united colonies are, and of right out to be, free and independent states, that they are absolved from all allegiance to the British crown, and that all political connection between them and the state of Great Britain is, and ought to be, totally dissolved. Okay? Again, this is saying that, hey, the colonies as states should just be independent and free, and the relationship between them and the crown now should just be dissolved and go away. This led to a committee consisting of Thomas Jefferson, John Adams, and Benjamin Franklin, Roger Sherman, and Robert Livingston. They were appointed on June 11th to take up the resolution. Okay, they were appointed on June 11th to take up the resolution. It's to draft a document declaring independence. So these are the men that will be working together to create and start the Declaration of Independence. So again, they would be working together. Give me 1 second. So on July 4th, 1776, in Philadelphia, the Declaration of Independence was unanimously adopted by the Continental Congress. Okay, this is the beginning of the Declaration of Independence. Thomas Jefferson, the chairman of the committee, was primarily responsible for the drafting of this document. So all those men that we talked about, they worked on it, but Thomas Jefferson was recognized as pretty much the official writer of the Declaration of Independence. And this was adopted by the Continental Congress on July 4th, 1776. This included the Christian elements in the Declaration of Independence are seen in the acknowledgement that God is the creator and sovereign of the universe. Okay, so we have some elements, some Christian elements in the Declaration of Independence. So Christian beliefs and stances and standards that we built into our declaration. Here are our Christian elements. So first, we have acknowledgement that God is the creator and the sovereign of the universe. Okay, we believe that God, He's the all-powerful being. We have the Bible is our source of truth, and that God is our source of power and knowledge, and that we are to trust in Him. Secondly, we have because man was created by God, individuals have true worth. Because man was created by God, individuals have true worth. It says in Genesis 1:27, sorry, I'm trying to pull it up real quick. Genesis 1:27, okay, so we're creating His image. It says this in the Bible. Genesis 1:27. It says, so God created man in His own image. It strictly says that right there. God created man in His own image. In the image of God created He him. Male and female created He them. Okay? So because man was created by God, individuals have true worth. Next, we have confidence in divine providence made the signers of the Declaration willing to risk their lives, fortunes, and honor. Again, confidence in divine providence made the signers of the Declaration willing to risk their lives, fortunes, and honor. Okay, by them signing this, and them being the people signing this and everything, This is going to put pretty much a target on their backs and their heads, right? So the British, as they're coming and their armies are coming, and we're going to see a war happen, we have these men that are going to be highlighted. Everyone's going to know who they are because they're on this declaration that's going to be for our country or future country. So again, these people are highlighted. They're going to be wanted men. So they risked and put the lives of maybe their families or anything at stake in jeopardy. And lastly, we have lastly, Christian element is it recognizes God as the supreme judge of men and nations. God is our supreme judge, right? The Bible says, "Vengeance is mine, saith the Lord." He has the last say. He has all power. He was at the beginning, and he will be at the end. And he is our supreme judge. And we use the Bible to decipher what is right and wrong. But that's all the notes we're going to do for today. I told you it was just short. Okay, we'll jump back into it on Monday. We'll finish the notes up on Monday. And we will review on Tuesday and test on Wednesday. But today, you do have that verse quiz. Distant learners, you should have those already. But I'll be coming down to the classroom to monitor that here in a minute. So you guys can review for a little bit longer. Again, it's Romans 13, 1 through 4. Fill in the blank. There's 25 blanks. Okay, so you don't have to know it word for word, but you have to know it fairly well. Hopefully it's not too hard. We'll be down there in a little bit. If you guys have any questions, let me know. Distant learners, make sure you're coming by later today after school. Turn in your stuff, and then I'll try to have everything you need for next week. If not, I'll just send it to you, and that will work as we've been doing it. Hopefully you guys can come back to school soon as Riverside County is opening up a little bit here soon towards October 1st. So we're praying and hoping that people can start coming back to school. It would be awesome to see you guys and get to know you more. But again, you guys, quiz right now, and that is it. There is homework as well. Sorry. There is homework as well. I was going to say no homework, but there's homework. I can't lie. So pull out a piece of paper. You're going to want to write this down. Homework is read pages 47 to 50. Read pages 47 to 50. Again, you don't have to read it word for word. We're going to cover the content in class anyways. But you're going to have to read it to finish the questions. And then page 50, you're going to be doing page 50, 7 through 11. Page 50, 7 through 11. Make sure you turn in any homework from last night. And that will be it. I'll be down there in a little bit for the verse quiz. So review for that. Make sure you have the homework done. If you have any questions, let me know.
All right, welcome to chemistry. Let's get right into it. We're on chapter 7, light, electrons, and atomic structure. And you're like, Mr. S, we just finished chapter 2. I know, I do things a little out of order. I'm a little weird. What are you going to do? But the reason I do this is because I feel like you need chapter 8 specifically. I think it's chapter 8. Yep. You need chapter 8 and maybe 9? Yes. You need chapters 8 and 9 in order to do chapters 3 and 4. So we may have a few things that we have to skip here in these, and then I'll cover them in chapters 3 and 4. But to me, they kind of put the cart before the horse in some things. So we're going to get right into chapter 7, light, electrons, and atomic structure. Okay, so again, we're going to come back and hit those other chapters. We're not skipping them. We're just covering the chapters that need to be covered first. In order. So, chapter 7 is light, electrons, and atomic structure. Now, before I can even deal with how the atomic structure works, I have to deal with how electrons work. Before I can deal with how electrons work, I have to deal with how light works. Before I can deal with how light works, I have to deal with how waves work in general. So this chapter is going to be building on itself the entire time, because in order to understand matter, we first have to understand light. So today, I'm going to be talking to you guys about 7.1, the nature of light, so that next week I can start putting all the pieces together for you guys, or with you guys, and we can start figuring out the pieces of an atom. So hopefully I've stalled long enough. You should be at chapter 7 by now. Chapter 7 in your textbook, it starts on page 93, and in your supplement it's on page 19 if you're still trying to find them. Okay, your supplement is in the order we'll go in class. Your textbook is obviously in the order it was printed. So that's just how that works. So the arrangement of electrons and atoms is one of the most important concepts in chemistry. For this arrangement largely determines the chemical properties of an element. The discovery of the electron helped lay the foundation for a revolution in chemistry, understanding why elements and compounds behave the way they do. It was not merely the discovery of the electron that revolutionized chemistry, however. Simply knowing that electrons exist is a first step, but it took decades of work by many brilliant scientists to discover how electrons are arranged in atoms, and how these arrangements determine the chemical properties of the elements. So before we study the electron structure of the atom itself, we must review the nature of light. Now, if you've been in physics, or if you remember from physical science, this may be a review, and that's fine. But we need to make sure that we all understand how light works, because that's going to show us how electrons work. As we shall see, the light and the electrons in an atom have several properties in common. In addition, the study of light and its relationship to the atom led to the most important breakthroughs in our understanding of electrons. So first thing we have to talk about is the properties of waves. And so, first of all, okay, in your supplement, you notice I have the definition for a wave, and then I just have this graphic up here while I'm talking about it. A wave is just a periodic back and forth motion that transmits energy. You're probably familiar with the ripples or waves that are produced when a calm lake is disturbed by a pebble or a passing motorboat. Waves in the ocean behave similarly. Water waves consist of a series of elevations and depressions in the water. The high points of a series of waves are called crests, and the bottom, or the low points, are called troughs. The properties of most waves can be defined by 4 terms: wavelength, amplitude, frequency, and speed. So first of all, let me see, what was that? Particle theory of light. Oh, that's way down there. Okay. So we're on here for a while. All right, so the wavelength is the distance between any 2 corresponding points on successive waves. So if we go from peak to peak, or from trough to trough, or even from the center line to the corresponding spot on the center line on the way up, that is a wavelength. Normally we do peak to peak, or crest to crest, or trough to trough, as that seems to be the easiest way to measure these things. In formulas and equations, the Greek letter lambda represents wavelength. That would be this character here that I am pointing to with the cursor. This one right here is lambda. Okay, it's spelled lamb, as in baby sheep, duh. Okay, so lambda. And this represents wavelength. Okay, it's kind of an upside down Y. It's not a Y. Make sure you pay attention to that. Okay, it matters in this class. So you have to make sure stuff is what we said it was. The amplitude of a wave can be considered the measure of the wave's strength. The amplitude of a water wave has to do with the wave's height and is equal to half the vertical distance between a crest and a trough. So If we draw a center line here, okay, the amplitude is how far off center we are, okay? So if I needed to measure and I didn't have a baseline or a center line, I could measure from crest to trough, divide by 2, there's my amplitude, straight up and down though. The frequency of a wave is a complete number of waves, crest plus trough, that pass by a point at a given time. One wave or cycle per second equals 1 hertz. Okay, and so you may hear us say cycles per second or something along those lines. That's the same as our measurement for hertz. So AC power in the United States is 60 hertz. That means 60 times per second, the power is going into the positive, then into the negative, then into the positive, then into the negative, then into positive, into the negative, 60 times per second. In Europe and other places, it can be 50 hertz. I forget exactly which regions are where, but many regions use 60, many use 50. It's a matter of which region's standard got accepted. In Japan, they have both. It depends on which side of the line you're on. So that's just one of those things there. So that's what all hertz means. It just means cycles per second. This is the SI unit of frequency. The standard SI prefixes are used to indicate multiples of this unit. For example, waves produced or passing a given point at the rate of 1,000 per second have a frequency of 1,000 hertz or 1 kilohertz. Another place where you'll hear this term a lot is in computer processors, where you'll hear, hey, we hit 5 gigahertz on all cores. And of course, now people are aiming for 6. And that's what that's talking about. That's talking about 6 giga. I think giga's billion. Yeah. So when they're hitting 5 gigahertz, they're hitting 5 billion cycles per second. 5 billion clock cycles is what they're talking about. A clock in computing is not the same as your clock on your wrist or on the wall. It's just the signal that says, okay, time for the next thing. Okay? And that's an oversimplification, but it's talking about it can do that 5 billion times per second. And so this is why modern computing is so fast. The next qualification we have is the speed. The speed of the wave is simply the rate at which the wave travels. Water waves usually travel at a speed of several miles per hour, while sound waves travel through air at about 740 miles per hour or 331 meters per second at standard temperature and pressure. You're like, what's standard temperature and pressure? We'll talk about that in one of those chapters we skipped. Okay, we'll come back to it. Light waves, the fastest waves of all, have a speed of more than 186,000 miles per second. Wavelength, frequency, and speed are mathematically related by the equation shown here on the screen. V equals lambda f, or more how we would read it, velocity is equal to wavelength times its frequency. For example, then, if the wavelength increases, the frequency must decrease if the speed is to remain the same. Well, this hopefully has been a good reminder of waves. Let's get into then the theories of light. So classical theories of light, there were several competing ones. The first theory of light to really come out, other than it being just there, okay, to actually think about light, is the particle theory of light. And this is the idea that light can be pictured as streams of tiny particles emitted by light sources. This was proposed by Sir Isaac Newton in his book Optics. And this theory seemed reasonable and became widely accepted in Newton's day. But not all scientists believe the particle theory. So, for example, the Dutch physicist Christian Huygens, I think I'm saying that right, a contemporary of Newton, proposed a wave theory of light, the idea that light consists of a series of waves rather than individual particles. Now, he was ignored for the most part at his time because Newton was such a big name in physics, and he invented calculus, and okay, he did a lot of things, so people just assumed he was right. And it wasn't until the 1860s when James Clerk Maxwell, let's see here. Yes, that's this gentleman here, showed that light can be accurately described in terms of an electric field and a magnetic field vibrating at right angles to each other, acting as a single magnetic wave. In other words, it wasn't until he proved Huygens right that the wave theory of light gained any traction. Okay? So the wave theory of light is the idea that light consists of waves rather than individual particles. And again, we call those electromagnetic waves. This is where an electric field and a magnetic field vibrating at right angles to each other. Again, James Clerk Maxwell confirmed this. Now, I'll mention this. Since this was proposed for light, we have since proven that anytime an electric wave exists, a magnetic wave also exists perpendicular to it. Anytime a magnetic field exists, an electric field exists perpendicular to it. Okay, and we'll just discuss that more. Oh no, we discussed that in chemistry in the magnetics chapter. So that's just something there. So you may notice, oh, I don't have an example with me. Anywho, you may have noticed on some cords, especially older, you know what, does mine have it? Is there one on rats? No, that would be too easy. On some older laptop cables or some other cables, you may see a weird cylinder, okay, near the end of the plug. And it just kind of wraps around the plug. And it's like, why is that there? Well, it's actually a magnet to kind of deaden the electromagnetic or the magnetic part of the electromagnetic wave coming down the line. So that way, all that really enters the device is electricity. So it's a way to cut down on the magnetism. So if you've ever, I really wish I had a cable with me that had it. I don't think, you know what, I do. All right, now how to show this, because I don't want to unplug my monitor. All right, you know what, this is going to be weird, but I'm going to do it. Okay. The things I'll do for an illustration. All right. Is that as far as I can go? Okay, on I'm committed now. Just don't want to put my laptop to sleep. All right, on this monitor, this is part of the power cord. Okay, I've got the power cord. Okay, power cord's coming in here, and then right on the end of it, it's a little too managed, I can't get it back out. All right, this little cylinder right here, it's actually a magnet. Okay, and the reason for that is because you don't want it picking up any of the magnetic interference from any other cables that might be running alongside or anything like that when it's delivering power to the device. Okay, so anything magnetic will always have an electric field. Anything electric will always have a magnetic field, and so on. Let me get this back correct here. Okay, so I know that was a bit of a detour, but you know, I like sharing interesting things like that. It helps connect everything. All right, let's get back to the notes. And I got to fix this because it's going to bug me. All right, hopefully that's right. So he figured out the electromagnetic wave part. That's why I had that up. Now, Maxwell explained that the electromagnetic waves behave much like... Right. Ah, I went to sleep. No. There we go. Okay. I forget. Okay, if I put my iPad on one side of my laptop, that's where the magnet sensor is for the lid, so it'll go to sleep. So I have to put my iPad on the other side. But anyway, moving on. All right. So this is the electromagnetic wave, and he figured out that they behave much like sound and water waves do. But that there are also some important differences. For example, sound and water waves require a material medium through which to move. But electromagnetic waves can travel through empty space. This is why we can see light from the sun, but we don't necessarily hear the sun. And that's actually a really good thing, because if we could hear the sun for even a fraction of a second, we'd all go deaf. Okay? Think about it. It's a giant ball of explosion. It's only 93 million miles away. Okay? And yes, I say only, because of the size of the explosion, we would all be deaf in an instant because it would burst our eardrums. Yeah, it's a really good thing sound can't travel through a vacuum. Anyway, Maxwell also calculated that all electromagnetic waves, every single one, whether we're talking light or electricity or whatever, travel at a speed of roughly 3.00 times 10 to the 8th meters per second in a vacuum. Okay, that's about 186,000 miles per second. Scientists represent the electromagnetic waves, including the speed of electromagnetic waves, including light, as the symbol c, where it is exactly 299,792,458 meters per second. The reason why it's exactly that speed is because we define the meter in terms of how far light travels in a second. So it's exactly that. For the sake of this class, we'll use 3.00 times 10 to the 8th meters per second. Okay, we're going to go and round because this gets to be a really big number and really a pain in the rear to work with. So that's what we're going to work with here. The speed of light, c, is one of the fundamental constants of the universe. The measured speed of light in a vacuum never varies. This is true regardless of the movement of the light source or the measuring equipment. More on that in the last chapters. Nope, other classes in physics. Anyway, we discussed it a little bit in physics. There actually is, if you're interested in relativity at all, I did an optional lecture at the end of last year in physics on my YouTube channel, Troubleshooting Mathematics. If you guys are interested at all, you guys can go back and watch that. It's heavily oversimplified, just letting you know. All right, so, back to this. As with sound waves and water waves, the frequency, wavelength, and the speed of electromagnetic waves are mathematically related. So c is still equal to lambda times f, or in other words, the speed of light is still equal to the wavelength times the frequency. Well, since c is constant, our speed can't change. As my wavelength goes up, my frequency goes down. As my frequency goes up, my wavelength goes down. They are related in that. Okay, so as long as we know one, we can calculate the other. We can also see from equation 7.2 that long-length electromagnetic waves must have low frequency. Oh, that's what I was just talking about. And while short wavelength waves must have a high frequency. Frequencies of electromagnetic radiation from less than 20 hertz to over 100 trillion megahertz. That's the range that we've detected so far. Wavelengths of low-frequency electromagnetic radiation may be measured in thousands of meters, while wavelengths in high-frequency radiation are commonly measured in nanometers. So this is a broad spectrum of ranges. And yes, I did use that word intentionally. Visible light actually represents just this little band of the electromagnetic spectrum. Maxwell actually successfully predicted that electromagnetic waves can also exist with much lower or higher frequencies than visible light. He reasoned that although these waves cannot be perceived by the human eye, they can be detected by scientific instruments. Years later, the discovery of radio waves and X-rays verified Maxwell's prediction. The arrangement of all forms of electromagnetic radiation in order of frequency and wavelength is the electromagnetic spectrum as shown here. The electromagnetic spectrum can be divided into 7 broad categories: radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, and gamma rays. Each type has properties determined by its wavelength and frequency. Now, I'm going to pause from the textbook here and just focus in on this chart because I'm going to dispel, oh goodness, at least 2 issues or 2 common misconceptions right now before we even get into further talking about it. First of all, the term radiation in mathematics, in science, is just the transmission of energy. That's all it means. So when we say electromagnetic radiation, this is a buzzword that I see all the time on news sites, and I facepalm every time I see it because you can tell the person got their degree in journalism, not in science. Okay? Because radiation is only the transmission of energy. And so people will talk about the danger of having the electromagnetic radiation of holding your phone up to your ear, and so that radiation then is going through your skull. Look, it just means the transmission of energy, and it's such a low amount, it ain't going to cook my brain. Okay? I could hold this here with all the Wi-Fi, cellular, all the other signals going to it until I'm 103, and it would have 0 impact on my brain. Okay? Mostly because the noise in the universe has been doing that for millennia. Okay, I'm out. All right, so there's that one. See, it doesn't just matter wavelength and frequency, it also matters your power intensity. So some things may share the same range, but the powers are very different. Okay, I'm gonna just, hold on, I'm gonna do a quick Google. Power limit for 5G. Okay, that's funny. Okay, that's what everyone's freaking out about. All right, so here's what we're going to talk about. We're going to go into this just a little bit, and then I'm going to get into the quantum theory of light before the end of the lecture, I promise. Hopefully. Okay, I will try to get to that, but I'm going to go on a rant here. And some of you are going, yes, sidebar. Yep. Okay, this is one of them. This is actually a planned one. Like, I actually plan heavily to do this one. All right, so couple things to note here. First of all, on the electromagnetic spectrum, okay, you'll notice that as we come down here, we go down to the lower ends. The electric power waves are 60 hertz. Now, just throwing this out there, human hearing is also based on cycles per second. Okay, now that's based on the movement of air through there, and not part of the scope of what we're talking about here, but just to illustrate this, human hearing is from 20 hertz to 20,000 hertz. Okay, so if air molecules get vibrated at any of those frequencies, we'll hear them. Okay, power lines are at 60 hertz. So if there's a 60 hertz interference in your electrical system, you'll begin to hear that low 60 hertz tone, okay? Because that's where the electric power waves are. Anyway, that's just as far as that goes. In normal power settings, you know you don't hear anything, okay? But you may hear it from things like fluorescent bulbs. You may hear it from things like audio equipment if it's not shielded properly, okay? Anything like that, really. The biggest one is fluorescent bulbs. That's where I mostly hear it now. And there are parts of this main building now where I can't hear it at all because we switched to LEDs, and it's amazing, okay? And that's just, it's one of those things. So down there in the modular, for those of you here in the Distance Learning Center, if you let the room get super quiet, you'll probably hear a low hum, okay? All right, I don't know if you guys could hear it or not, but I just wanted you guys to kind of get that idea. We would actually have this problem really bad in our auditorium here, to the point where every now and then Pastor would think our sound system was buzzing. And I'd have to tell him, I'm like, Pastor, I could turn off the sound system right now, it would make no difference. And instead I would go over, turn off the lights, and boom, silence. It was just they were getting so loud because our ballasts were so old. So that's part of the ones that we changed to LED, and it's been wonderful. But anyway, so that's enough about that. But then we come in as we go from really long wavelengths to shorter wavelengths or to higher frequencies. We get into radio waves. And so you'll notice AM radio is actually pretty low on the spectrum. I mean, it's really far down here. And that's in... Anyway, so this is where AM radio goes. And then, so the numbers on your radio station, they aren't arbitrary. Now, if you have satellite radio, those are completely arbitrary, okay? But if we're talking like standard radio in your car, those are not arbitrary. Those are the actual frequency it's being transmitted at on the radio. This is actually the frequency on the spectrum they're being transmitted at. Now, I will be upfront with you guys. This is an older chart, so it shows FM and radio and television. And television has taken up this broad spectrum. Okay, since television has gone digital, this has shifted and been shrunk just ever so. Well, actually, it was pretty drastic. So that was. Oh goodness, has it been that long? That was over a decade ago now. Anyway, for the longest time, FM radio was just a slice of the television thing, and altogether that used frequency modulation. As a matter of fact, old school. This is before digital, so I guess, yeah, it's been a while. But back when television was set analog, the audio was just FM transmitted. Anyway, you'll notice cell phones, radar, GPS, wireless networking, and microwave oven are all next to each other. And you might look at that and become immediately concerned, like many people do when they read an article on the internet without doing their homework, about having something that works in the same range as a microwave oven up next to your face. This is what I was talking about. And so the idea here, okay, between GPS, wireless networking, that would be specifically, this is the 2.4 gigahertz. There's also a wireless networking slice right around here now. That's a fairly recent development within the last decade where it really gained popularity. Let me put it that way. Okay, so yeah, and then you have microwave oven right here. Okay, so two things to point out here, and I'm going to point out one thing first, and then I'm going to discuss why we shouldn't be worried about it, okay? Why we shouldn't be paranoid about it, let me put it that way. The first thing to notice is this is why if you've ever been, decided to go make popcorn and then say Netflix started buffering, or if you're using wireless earbuds and all of a sudden the audio starts to sound really garbly while your microwave's on. I don't know if you guys have that problem. I've had that problem before. I'm also in an older house. That's because they're on the same band. And so when a microwave's going, it will disrupt 2.4 gigahertz communication because a microwave oven is using 2.4 gigahertz. And part of the FCC rules is that devices have to accept interference. So, and that's actually a good thing, by the way, and that's not the scope of this class at all. I'm already going way off scope, and I don't care. So that's why, though. That's why it disrupts it. So I've had to, back when I was able to see the TV from the kitchen, I would sometimes try to throw in a bag of popcorn and then come over and keep watching the TV show on Netflix or whatever streaming site it was. And, and then it would start buffering like crazy. And I'm going, what in the world? And then I remember, oh yeah, the Wi-Fi router's in the other room. It basically has to go right by the microwave to get to the TV. So our service would get disrupted. So that's why, if that's ever happened to you. I don't know if it has. I have, again, older house, so maybe not. But that's why. So now I told you guys we shouldn't have to be concerned even though they're in the same spectrum. Just because they're the same wavelength does not mean that they have the same power. For example, okay, the new 5G that everyone's concerned about, and people are actually starting to light 5G towers on fire. They did the same thing with 4G. They did the same thing with 3G. They did the same thing with cell phones, okay? People will always overreact to something new because technology is evil and, let's all be run away. Okay, seriously, I get really tired with this argument. To me, it's the same thing as like someone looking down at someone for using a digital Bible in church. I'm sorry, is the fact that it's on a screen any less inspired? Anyway, moving on. Okay, technology is not inherently bad, and again, I'm getting off that topic because I'll rant on that one all day. The reason we don't have to worry about it, okay, is because the different power intensities. For example, even 5G uses at most, the worst case scenario, 120 watts at the transmitter. That means if you stood right next to the transmitter, you'd have about the same energy as a really bright light bulb. That's it. That's all it is. Realistically, they use between 250 milliwatts and 120 watts. So very small amounts of power. Versus a microwave oven, which start for the low power ones at 700 watts. Okay? We're talking over 7 times the power of a cell phone tower in a tightly contained little box. Okay? When you turn on a microwave, you're not releasing microwaves into your kitchen. Okay? You don't have to worry about like putting a skillet in front of you or something. You don't have to worry about any of that, okay, because it's all shielded. Okay? It all bounces off the surfaces in the microwave. Okay? And that's how that works. And so realistically, most microwave ovens are on the order of 1,000 watts or 1,500 watts for some of the higher end ones. Okay? And so that's what we're talking about here, is we're talking massive amounts of power. That's what makes a microwave oven work. It just so happens to use things in the same frequency and wavelength. Okay? Again, versus the maybe realistically on average, by the time it gets to your cell phone, at most 1 watt of power, whether it be from Wi-Fi or cellular. 1 versus 1,000. Let me think about that. Okay, and then ironically, then we get to the microwaves. I love that. The microwave oven is not even using the waves in the microwave band. It's very close, and so I get it for marketing. You don't want to call it a radio oven. That would have freaked people out back in the day. So anyway, that's microwaves. Then you have infrared rays. You often feel this as heat. Okay, so this is why infrared cameras work, because they're picking up on the way heat gets transmitted. So when you're out in the sun and you feel that warm glow, you're feeling the infrared rays. Your eyes can't pick up on it. Your skin can feel them. Okay? And then we start getting into visible light, where we go from red, orange, yellow, green, blue, and violet, where violet is actually the most intense or the most energetic wavelength that is realistically safe. And so this is why it's concerning that they're doing more studies, and they're finding out even blue light might actually be damaging to your eyes. And the studies are still being done on that. And so I'm going to reserve judgment because I've seen studies that have gone both ways. And so I'm going to reserve complete judgment on that one. Other than, okay, blue light filter at night, I have noticed that helps, okay, as far as falling asleep. So there's obviously something to it. I just don't know if it's quite as drastic as some people will lead you to believe because, marketing. So with that, okay, then violet, and then you get into ultraviolet, and then you'll see UVA, B, and C a lot of times. Oh, sorry, real quick. TV remotes are in that old infrared spectrum right before red. So that's why you don't see a beam of light normally, because it's transmitting through infrared. And that's why it needs a direct line of sight, because you're literally transmitting light at the screen, okay, unless you have one of the new Wi-Fi remotes. And then UVA, B, and C on the other end of visible light spectrum. Again, notice how close these are. All visible light is right in between there. UVA, B, and C are what can actually start to burn your skin. That ultraviolet light is extremely powerful, extremely energetic. And the more energetic, the less power you need to transmit it at to do damage. Okay, and so this is why these higher ones can do a lot more damage, even if we're doing lower powers. So, as we continue on, by the way, good sunscreen should block against all three. Many of them will only say UV, A, or B. A lot of them will omit C, and you need all three. But anyway, so that's ultraviolet light, and then we go into X-rays. That's where that's the spectrum we use to get X-rays. I don't know what else to tell you about that. Okay, we were very, very specific with our naming. And then gamma rays, we can use them with PET imaging, and we can use things along here. This is when you start getting to actual radiation. Specifically, gamma rays are often a byproduct of actual, like, nuclear radiation. Okay, and we can use it for like PET imaging and things like that. Again, in small doses, you're fine. Okay, but that's really the spectrum. And so hopefully this gives you a better picture of the spectrum. Hopefully it gives you a better understanding of what can make something dangerous or not dangerous. It's not just where it is on the scale, although that does matter. Obviously, you want to avoid UV light. You want to avoid X-rays and PET image and gamma rays, unless it's for a medical procedure where you're going to be a controlled brief exposure. You want to avoid those because they can damage you, even at similar powers. Relatively low, that's the word I'm looking for. However, down here, you have to crank the power up a lot to get it to do the same thing. Now, I'm not suggesting we switch microwave ovens to gamma ray ovens to save power. Okay, that would be a bad idea, bad time. But I'm just saying there's a huge difference between a 1,000-watt microwave oven versus your 1-watt maximum receiving power on your phone. Okay. By the way, for reference, a typical 2G, 3G, or 4G antenna uses a transmission power of about 20 watts. But again, that's at the transmitter. That's if you're standing right at the tower. None of us stand right at the tower. Okay, so realistically, by the time it gets down to us, it's 1 to maybe 5 watts. Okay, so really not a whole lot to worry about. Either way, it's less than 20. So I know that was a bit of a sidebar, but I enjoy going through the electromagnetic spectrum because it helps unlock some understanding, and I hope that this has done that. Now let's go on to the quantum theory of light. Okay, now the word quantum is, oh goodness, it's a word that's been hijacked lately. And don't misunderstand this, but specifically Marvel has really hijacked this word and completely twisted it. And to be clear, I enjoyed their use of it. I just wish they hadn't called it that. Okay? Because quantum isn't just the name of subatomic realm. Quantum means so much more than that, and I feel like they didn't show enough respect to the word in that case. Okay? And I know that sounds dumb on the surface, but as someone who actually understands what quantum means, it was very disappointing, let's put it that way. And so specifically, the two gentlemen who showed that light has characteristics of both light and waves are Max Planck and Albert Einstein. Now, usually we consider Albert Einstein to be the father of relativity, but Max Planck did quite a bit of work too. And both these guys showed that light cannot be classified as simply particles or waves. It can't be one or the other. Because if you treat light like particles, it behaves like particles. And if you treat light like waves, it behaves like waves. And both can't be true at the same time. Can they? Well, it turns out they can. And so basically what we call this is we call this the wave-particle duality. This is the two-sided, both waves and particles, nature of light. And the way that we deal with this is we have introduced what we call the quantum theory of light. And this is the modern understanding of light. And this states that the light consists of tiny packets of energy called photons. And the way you could think of this is an envelope full of that section of wavelength. I know it sounds dumb, but I'm working with something that's really hard to explain or understand. Okay? Because light is, yes, it's a wave with discrete amount of energy along the way. It's countable. And that's actually where we get the word quantum. The word quantum is the singular in Latin for quanta, which means to quantify or to count. Okay? All quantum means is that it's countable. That's it. And so the idea of a quantum realm is just almost absurd. And I get why they did it, and it's great sci-fi. Don't misunderstand. And I thoroughly enjoyed the story part. But it's not a thing. But see, you have the quantum theory of light, and this states that light consists of tiny packets or energy called photons. And the idea is that you could potentially count these photons because they're discrete packets. Okay, again, discrete in mathematics just means countable. The amount of energy a photon contains is proportional to its frequency. When interacting with matter, photons act like particles, but when traveling through space, photons act like waves. This would also be why electromagnetic waves can travel through the vacuum of space, because it is its own medium. It is its own particles. Although light is often difficult to describe, this theory allows us to define light as electromagnetic waves traveling as photons. A consequence of quantum theory is that light must consist of whole numbers of photons. A half photon cannot exist. As an analogy, when you go to a local fast food restaurant, you may order 1 hot dog, 2 hot dogs, or some other number of hot dogs, but I highly doubt you'd be able to purchase 1.28 hot dogs or 3.42 hot dogs. They must be ordered in the whole number multiples of the basic unit. According to quantum theory, the energy of a photon is directly proportional to its frequency. So the energy of a photon is equal to Planck's constant, okay, which is h, and that value is given there on the screen. And the frequency is represented by f. Since only whole photons can exist, the total energy of monochromatic or single frequency light must be a whole number multiple of h times f. So again, that quantum theory of light is talking about that it's countable and that it's both its own particles and its transmission of energy. I hope that's made sense, largely because 7.2 depends on that making sense. If you guys have any questions, feel free to text or email me. I highly encourage you to go back and reread 7.1. This is one of those concepts that it's very important that we get because it's going to define even how we look at the electron. Okay, and most of chemistry is dealing with the electrons. Okay, we won't necessarily be concerned with, okay, and I'm dealing with this electron and that electron, but indirectly we're dealing with electrons. And so that's what I want to focus on, or wanted to focus on today. All right, tonight's homework is 7.1, which is, if you go to pages 23, or page 23 first, page 23 on your supplement, you guys have questions 1 through 4. But then if you turn over to page 26, you'll notice we have a section of problems. Okay? And your homework will always be broken up where your questions are first, then your problems. And so then in 7.1, you have 3 problems on page 26. So you guys are doing the 7.1 questions and problems tonight for homework. Again, if you guys have questions, feel free to text or email me. I will not be down in the Distance Learning Center today. I've used up all my time. I can try to answer more questions on Monday if needed. All right? You guys have a great weekend, and I will see you guys later.